All right, getting started. And again, I'm just going to wait a minute to see if I can see it on the stream because I don't trust nothing. Sorry about the audio. Last week, I had turned off the monitor on, I have multiple mics, and I turned off the monitor on one of them, and I thought that meant that I turned off the mic, so I turned on another mic because I was like, oh, I can't hear anything. And it was awful. So, welcome to the stream. If you saw the title of the thing that you're watching now, or you saw my discussion on Twitter, we're going to be talking about turning raw text into structured data. And what I mean by that is, it's one of my pet peeves when people say, oh, text isn't unstructured data. So if you just have a string of text, and let me start a kernel so I can write down my thoughts. I was actually going to put together like a lesson plan and a bunch of content, and I had a really hard time focusing on things today. There was just a lot going on. So I didn't do any of those things, but I do have a general idea of what I'm going to say. So text into data. So the idea is that if you have a string of text, so no, let's actually type some real language. This is a string of text that is single quotes, unstructured. This is a string of text that does have internal structure that we can understand as human beings who use language, right? We know that in some sense, this of text piece is related to this string piece in some sort of hierarchical relationship. And you may not know this like consciously, especially if you haven't studied grammar or you don't speak multiple languages. But there is some sort of relationship there that is also, you know, the verbs have relationships to the noun. So if I said this is strings of text, you might be like, oh, that sounds a little bit weird. I'd expect, you know, this change in the one part of the language to have a follow-up change on the other part of the language, because I've heard lots of examples of that. So there is internal structure in any natural language data. The problem is computers don't know about that, right? So to a computer, if I have stored this string of text, this is just a byte string. So even though there is, you know, important structure here that as a human tells me something about the world, it's hard for a computer to know that. So the field of natural language processing is basically turning words into numbers, and there's a lot of ways of doing that. And so what I'm gonna talk about today is basically how to turn words into numbers, and what that means, and some approaches, and how to turn, you know, text, which is from a computer standpoint unstructured, even though we as humans do know that it is structured. Again, sorry, this is just my hugest pet peeve, into something that is structured from the computer's point of view in a way that is consistent with what we as humans know about text as we're interpreting it. So that's the general idea of what we're going to talk to today. And I have actually I haven't stolen them, some slides about this. So if you are not familiar, I've got a copy here, like an actual physical copy of the book. It's very large. The most common introductory text to natural language processing is Speech and Language Processing by Jurafsky and Martin. And it's a good read. Like, I've read a lot of textbooks. It's, you know, enjoyable to read, pretty easy to follow. Wow, that text is super, super small for y'all. And the most recent version of it is actually available online. So these are the slides for one of the chapters that we're going to be looking at now. And you can see I've gone through and sort of read some of the newer chapters just because I was like, oh, what are you saying about it? I want to see, I'm nosy. And I have lots of respect for Jurafsky and Martin for putting the text online so that people can access it, which is great, good for the field. And these are some of the slides on basic text processing. So text processing is what I would call this sort of process. I might even call it pre-processing, depending on what exactly you're talking about. And word tokenization is sort of the first big subject in here. Actually, the first big subject is regular expressions. I would strongly recommend against relying heavily on regular expressions in a natural language processing workflow, just because they're hard to read as a human, they're hard to interpret, and it's really easy to make weird mistakes. If you've ever read like a book or a paper and maybe every time that there were miles in a document, they replaced it with kilometers, right? They just went through and did copy and paste. And that's something you would do with regular expressions, which is fine, but then the word smiles is the word kilometers, and that's not a real word. You did actually mean smiles. So it's really easy to make that sort of like weird mistake if you're using regular expressions. I certainly do, so we're skipping them. It's good to know. It's an important skill. I wouldn't recommend building an entire pipeline around them. So, tokenization. The basic idea of tokenization is that you have a string of text. So again, you have this byte string. This is a string of text that is untextured. And at the computational level, there's no way of telling that these 4 characters are more closely related to each other than these 4 characters, right? Even though we as human readers know that S space IS means nothing. Vishnu says, but regular expressions are used extensively in information retrieval systems. Yes, I also use them. I'm not saying never use them. I'm saying that if there's a tool that will do what you're trying to do with regular expressions that someone else has already built and done like unit tests for, use that tool instead. It will be faster and easier, and you will be a happier person. And I say this as someone who has made themselves very unhappy by over relying on regular expressions. It's regular expressions are like they're like a screwdriver, right? And there's nothing wrong with a screwdriver, and sometimes what you really need is a screwdriver. But if you have like a power drill and all you're doing is putting in screws, use the power drill. Vishnu says, is there an alternative for open source projects? It depends on what exactly you are looking for. So if you're trying to do something like, what sort of task are you looking for, Vishnu? Like, what is it that you are hoping to use regular expressions to do in information retrieval? I'll give you a second to answer, because I know there's lag on my side, and also then you have to type. But the general answer that I would give here is, if it is a common task that you are doing, for example, I want to identify all addresses in this string of text, then yeah, probably. If need to answer specific questions. Oh, for question answering. Yeah, question answering is its own thing. For that, I would use a question answering system if one's available in the language that you're working with. So the problem is that there are a lot of tools that have been built, which is nice, and they generally assume that you use English and that you are working with English data only, and that is obviously a huge problem if you speak any other language. Yeah. Vishnu says, say I had a use case where how many percentage of records have a particular term? Ooh, we will get to that today. So I can stick around. I'll tell you the answer. Sorry, I'm trying to scroll up one because I saw somebody else said something. TGB says, hi, I have a lot of text and would like to make sense of it. Where can I start? TGB, I usually use R. Well, we're gonna get through there. So the process I'm talking about today would apply whatever language you're using, Python, R, Perl. A lot of like old school NLP is in Perl. I know there are still people who are teaching intro, undergrad NLP in Perl, which I would not, but that is their choice as an instructor. Yeah, so we'll talk about I'm gonna answer both of your questions, but it's gonna take like half an hour. We will get there. Okay, so I was saying about texts, strings of characters. So we want the computer to know that these 4 letters are more closely related than these 4 letters, right? And that this is a chunk, and we might call it a word. It might be something with a contraction, so it might be several words together. It might be like important white space, so it might be like a chapter header that has, you know, two carriage returns in it, and we want to treat that separately. But the process of saying, okay, these are the language units that we're interested in is called tokenization. So if you just have running text and you need to say this bit's something, this bit's something, this bit's something, tokenization is the process of doing that. TGB says, basically, I have to use the text data to gain some predictive power and then use that in a classification system. Hope you can touch this topic. Thanks. Yeah, what we're going to be talking about now is how to take the data, the text data, and turn it into a form that you could use as input to, you know, your classification, your regression models, your whatever. So the tokenizing step is pretty straightforward in languages like English, because usually you're going to have a space between words. So let me actually put in a cell here. So step 1 is tokenizing, splitting the text into units of language. So in English, this could be words, and you can split them on spaces. That is sort of the easiest scenario, but there are lots of languages where that's not going to work. So German, for example, I don't know if any of you speak German, but if you just sort of like look at some German text, let's see, German language text. I just want to see some German text so I can make my point. Here we go. So if you just look at some German text, you can maybe tell that the words are like a little bit longer than they are in English in general. Actually, let's find enuctatute text. Another example of a language that would look like this would be enuctatute. So if we look at this, here's some sample enuctatute, and it's actually written in the Canadian syllabary. So each of these symbols is a syllable. It's similar to the Korean writing system, if you're familiar with that. It's another syllabary. So this word is 1, 2, 3, 4 syllables. This word is 1, 2, 3, 4, 5, 6 syllables. This word is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 syllables, which is a pretty long word. This is another really big one. This is another really big one. These are much, much longer than English words. And the reason is because this is a language that's agglutinative. So in English, we might say, I went to the shop and I came home quickly, and that's a bunch of words. In enuctatute, which I don't speak, you might say something like, I went to the shop as one word. That just has a bunch of like little meaning morphemes. That's what we call those little units. So like the S in cats, that means I have more than one word. And we squish a bunch of them together and we get a really long word that has a sentence worth of content in it. Or, and I returned home quickly, we might have another single word that tells us that we did this in the past, but after another event. We might have another word that says that you did it, another morpheme in the single word that says that you did it quickly. You might indicate cardinal directions in the words. You might say returning home, going to the east, maybe. I don't think enuctatute has that, but lots of languages do. You might have the fact that you know that you did it because you did it as an individual rather than you saw it or you heard about it or someone else told you about it in this word. So you have a lot of information in a single word. And because there's so much information, those words are likely to be completely unique in a text or a corpus. So instead of breaking them into words, you break them into morphemes so that you can say, the morpheme for home is in this word, and the morpheme for home is also in that word, and then this other word, and there's 3 times that it occurs in this corpus, rather than looking at these really long, very informative words. So you can't always just break apart on spaces. The other place where you're going to run into problems I shouldn't say run into problems. Like, it's not like some languages have problems and other languages don't, and those are the good languages and we like those ones. There's just assumptions built into a lot of tools that can make it difficult for people who are not trying to work with English text. So another thing that can be a problem is, a challenge, I should say, is, can I see this PDF? Are you open source? Yeah. Nope, I can't. It does say open access, but I did not see the PDF, and it didn't get downloaded either. Anyway, languages that don't have spaces between words. So in English, we have spaces between words. In Inuktitut, they have spaces between words. In German, they have spaces between words. This is one way to show that there's a difference between words. In a lot of languages, you don't have that. So Chinese word segmentation is probably the most established task in this group of tasks. And in many Chinese languages share the same writing system, which is based on characters. So a single character can be a word on its own, or it can be, much like when we were talking about Inuktitut, you can have lots of morphemes together. It can be part of a longer word, and you don't necessarily know when you're just looking at a text, if you're not a Chinese language speaker, where the boundaries are between the words. So Chinese word segmentation is this problem of tokenization, of being like, here's all the little units that are important. So just like we want to say that these units are very related to each other, these units aren't, but using Chinese characters rather than Latin characters, and also without spaces. And it's not just Chinese. I think Japanese doesn't have spaces either. Thai doesn't have spaces. It's fairly common in Asia. That's the word I was looking for. You know, the continent. It's fairly common in Asia to have languages that don't have spaces. Does Amharic have spaces? Amharic might not have spaces either. And Amharic is spoken in Ethiopia. I can't. Yeah, I think there's spaces in there. I think it's not just me being dyslexic. I think that's a space and that's a space. Yes, so lots of languages don't have spaces, which means that you have to do a lot more work to figure out where the boundaries are between words, or between these meaningful units that you're interested in. Why do you want to know about meaningful units? Because the way that we turn words into numbers is that we identify all the meaningful units, and then we count them. And if we care about ordering, we also maintain information on the way that they're ordered. We don't always. So you might have heard the term bag of words. Christopher says, as a beginning Chinese student, that was indeed a bit tricky. Sometimes there are also several ways you can break it up. Yes, absolutely. Yeah, I have spent many years studying Chinese. I think I got the lowest grade in any class I got in college in Chinese, and it was because the writing system is very difficult. There's a reason that China has a scholar class, and it's just a really, really hard to learn writing system. Which is not, like, I don't want to say that there's a value judgment there, it's just, for me, it was extremely difficult. I think I can recognize like 5 characters now. I've just like, all of that work is just like, right, counting things. So you might have heard of the term bag of words. And this is probably the easiest way to get started with any sort of NLP task and turning your words into, turning your text into data that you can work with and feed into a model, is you can consider each word a feature. So every word that you have in your corpus is a feature. And then if you look at your subtext, for every word, that you have, you count the number of instances you have in that subtext that you're interested in, and then that's your feature set, the number of times each words occur in a specific subtext. And there are lots and lots and lots of techniques that you can do with this. Topic modeling is usually based on that sort of like, you know, number of words, language identification, some approaches to that. So like I hand you some text and you tell me what language it's in. Sometimes it's done at the character level as well, if it's a language that uses, you know, like Latin characters. Lots of ways to do that. You can also, instead of counting individual words, so instead of counting this and then is and then string and then of separately, you can count what are called Engrams. So an engram is, n is just a number here, and then the number of words. So this would be a bigram, 2 words. This would be a trigram, 3 words. This would be a unigram, 1 word. And this would probably be a 4gram. People don't really say quadgram. I guess you could say a tetragram, maybe? I don't know. I don't really hear it. I'm sure someone somewhere says it occasionally, but not when I'm around, I guess. So this would be a 4gram, 5gram, etc. The reason that you would do this is that there is, in addition to individual words having meaning, I think we all, as speakers of language, are not surprised to hear that words have meaning. The relationship between words is important. And if you don't want to devote a lot of time and computational resources to that relationship, if you've decided that that's not a priority for you, you don't need to know the relationship of every word in this sentence to every other word in this sentence, then a sort of computationally cheap way to record the fact that there is a specific relationship is to use this Engram method. And instead of counting just this, you count this is a string of. So that's how you would do bigrams to chunk it up. And in that case, instead of your data structure being every word and then the number of times it occurs in a text, it would be, you know, all of your Engrams, whatever you're using, bigram, trigram, and then counting the number of times each Engram that you are looking at occurs in each of your texts of interest. As might be obvious, those are going to be a little bit sparser. So if you think of all the words in the English language, there's, I mean, a lot. People don't use most of them. But if you think of all of the possible combination of 2 words together that people have used, there's a lot more of those. So if you have especially a very large data set, you are likely to have the bulk of your data set be, you know, Engrams that only occur once. So maybe a string, or maybe string of. A string would probably be fairly common. Maybe string of only occurs once in your entire corpus. And then, of course, you have to deal with data sparsity, which there are lots of other resources for learning about. So to recap what I was just saying, so one is can use words, works for languages like English, but it's harder to segment languages without a character to indicate segmentation, like Chinese. And the other thing is you can use morphemes, which works well for morphologically complex. Morphologically complex languages like German or Inuktitut. Inuktitut. Yeah, that looks right to me. That may or may not be right. So that's sort of the first step, is just to cut things into chunks. And obviously you need to tokenize before you do your Engrams, because if you don't tokenize, you don't necessarily know that this is one chunk, this is one chunk, this is one chunk. And if you don't know like where the chunks are, then you can't say, I want 2 chunks, I want, 3 chunks, I want 3 chunks. So tokenization is always going to be your first step. I think that's all I have to say about that. And the way that you do this is you use a tokenizer. Use a tokenizer for this step. And the best way to find a tokenizer is just to Google for one. So if I was interested in a Chinese tokenizer, I could Google for one, and I can find several of them. So there's Chop, which is for Python. There's Chinese word segmentation, also I search for Python. There's Chinese Tokenizer, which is on PyPI. More Stanford Core NLP. There's some stuff from NLTK, which is the Natural Language Toolkit, which is probably the most commonly used library for research. LingPipe, Chinese tokenization, and word segmentation. So there's a lot of options, and you just have to know the name of the tool. Okay, that's one thing. So that is the first step of counting. The second problem that you're going to want to run into, that you're going to end up running into, is stemming. Figuring out that different forms of the same word are the same. And this is going to be more of a problem when you are working at the word level than when you're working at the morpheme level. That's probably how you spell figuring. That looks okay. So an example here is if I have, okay, here's a good example. So unstructured. Unstructured has 3 morphemes in it. So these are those little subword, I mean, they can also be words. These are the smallest unit of meaning. So we've got un, which means something like not, reversing whatever the rest of it is. We have ed, which in this case means something like having the quality of being. And then we have structure, which means something like, God, I'm not a lexicographer, I can't just come up with word meanings. Having organization internally where parts relate to other parts. Well, I don't know, something like that. So there's 3 units of meaning in this word. And the reason that we want to be able to figure out where the boundaries are is because we want to know that words like structure, oh my God, I should have picked something easier to spell. Structuring, oh my gosh, structured, structurable. That's probably a word. Probably not the way I've spelled it, but you get the gist. So I want to know that all of these words share a root. And there is no down caret because I am not beloved of the gods. I would really love a down caret. Unicode? I think there is a down caret, but I think it might be a joining character. Anyway, so I want to be able to say that there's something about the word unstructured that also exists in structuring, that also exists in structured, that also exists in structurable, and that also exists in structure. And that these all have a relationship to each other. And for something like structure, you're like, okay, I guess, but what about things like ran, right? If I want to count the number of times somebody talks about running or having run or being run over or ran to the store or running, I think I'm repeating myself there, but if I want to say that all of those things are the same and I want to count them, then I need to not just look at the way that the individual letters are arranged and match the arrangement of individual letters. And this is where to talk about regexes, which I think it was Vishnu brought up earlier. If you're just using regexes, it can be a little bit hard to find all of the matching sets. So with structure, you could probably like search for this little span and get most of it. But for things like ran, run, running, or the classic example, sing, sang, sung. What's up, German? We've got the same root, the same meaning. These all have a relationship to each other, but the spelling is different across them. So what stemming, that different forms of the same word, that different words share the same root. So what stemming does is it figures out what the root is, and it also figures out what the morphemes that are not root morphemes, which have a word for them, which, oh my god, I can't remember. Oh my god. Root. Stem. They're gonna take away my PhD. What's it called? And I don't have a textbook within arm's reach. Well, the other ones. The ones that aren't the root morpheme. I'm gonna lock my door so the PhD police can't come back and find me. Anyway, so discovering what part of the things of it are chunks. Yes. TGB says, it's very late in the UK, but I'm really enjoying and learning from the stream. Will the stream be available in recorded form on this channel? Yep. Pretty much as soon as it's done, it'll be up. And all of my live streams should be up, and they're in the Kaggle Live-Coding playlist. Yeah, that was the biggest thing about Twitch when I used to do it, is that the videos just go away after 2 weeks. And I was like, well, then I can send people links and be like, I talked about this 3 months ago. Here's a helpful link. Yeah, so the stemming lets you count better. You're very welcome. And then talking about counting, I know that there's a place where he talks about stemming in here. Oh, here we go. And just like more issues in tokenization. Like I said, I didn't do a lot of preparation for this one because, again, just other things were in my brain space. So how do you tokenize this? Is this a separate word? Is it its own thing? Is it part of Finland's? Is Finland close to is Finland's the same as Finland? You know, hyphenization, all sorts of you know, oh, he does talk about German. Okay. All sorts of things that are problems there. Actually, I should go back up and see what the third thing was. So, how do you stem? Now that you know there's a problem, what do you do? And to do this, you use if you tokenize using a tokenizer, you stem using a stemmer. Use a stemmer for this step. This is only going to be a step for languages that have a morphological complexity. I don't think there's actually an E in there. That looks better. And the way that you stem is using a system of hand-built rules, usually, because of things like, especially in English, ran, run, running, sing, sang, sung, things that have a root where there are changes. Vishnu says, in my case, I had a hard time finding all the combinations of misspelled words especially and adding them to regular expressions. Stemming changed all correctly spelled ones. Any suggestions? Yes. Okay, misspellings. Let me see what I can find. So for misspellings, what I will usually do is fuzzy matching stemmer. Yes. Help me out. Blah, 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 fuzzy match and stemming. So fuzzy matching is, so regular expressions do exact matching. So if I'm like, I want words that start with S and have 4 letters, I will only get words that start with S and 4 letters, and I will not get anything else. Fuzzy matching lets you find things that are similar. So I might say, I want things that start with X and have approximately 4 letters. And it will basically, it sorts things based on the edit distance. So how many individual characters you have to change to get from the thing that you asked for to the thing that you actually get. And I'm sure Oracle will help you out with that. I'm sure pretty much any cloud service will probably help you out with fuzzy matching. Blah, 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 blah. Stemming, blah, 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 blah. This is not actually helpful. This is how to use their product and not information on the thing. Fuzzy and Elasticsearch, blah, 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 blah. Yeah, so what I would probably do is, yeah, I'm thinking. So, misspelled words. I'm gonna start a new section. Challenges. They may be unique, which is hard because you can't just look at only unique words. There's this thing called Zipf's law, word frequency. So that's not a great image because that is in log and I want it in raw. There we go. So the idea is that most words, what if you were bigger? Yeah. So most words, if you were looking at the dictionary, most words in the dictionary are going to be very uncommon, and very few words are going to be the bulk of the words that you see. So in English, words like a, and, the, of, what we would call function words, make up the majority of the words in any given text, and very rare words are going, and most words are going to be very rare, if that makes sense. Hopefully I'm making this clear. It is last thing on a Friday. So you can't just look for unique words and be like, oh, all the unique words are misspelled. A, because you might have misspellings that are very common, so like t for the, and B, you might have unique words that are perfectly fine. So tokenizer. Tokenizer is a very rare word, but it's a perfectly fine word that does have a meaning that I don't think I misspelled here. I might have misspelled it. I'm not very good at spelling. I am dyslexic. So you can't just be like, oh, I'm going to find everything that's unique and then use fuzzy matching to find the closest thing. Yeah. So that's a problem. The other thing is they may not be very like the intended word. So if you've ever, done a Google search and you spelled it bad, which happens with like 90% of my Google searches, and then the top recommendation, I'll get it later, the top recommendation is something that's not the thing that you intended it to be, and the thing that you actually meant to type is like the 4th or 5th recommendation. It can be hard to know just looking at a word what it was supposed to be. It's easier if you have a long stretch of text, but even then you're going to have, you're going to have problems with looking at things by hand with your eyes, because that doesn't scale well. Ask me about looking at things by hand with your eyes rather than automating things. I did a project by hand that I should not have done by hand, but oh well, I learned a lot. Yeah, I haven't actually done a whole bunch of work on spelling correction, so spelling correction for stemmers. And this is a problem for, don't mind if I do. I think I actually have heard about this, this package, I just haven't used it. So tell me about your spell check. Spell checking. You have a dictionary word affix combinations for incorrect words. Okay, so it looks like this package will do both together. yeah, I guess that's my recommendation, is to use Hunspell. The spelling package builds on Hunspell and has a wrapper to spell check. Okay, so there's also a whole second package you could do if you were interested. And analyze function returns both the stem and the affix syntax of the word. Affix, that's what it is. That's the other thing. Oh my gosh. Whew. Vishnu says, e.g. in a chat corpus, and the rep is typing the follow variations for address, and it's spelled a bunch of different ways. Yeah, see if this works. Yeah, generally I would not recommend building things yourself. Yeah, that might help. I don't know, give it a try. Oh, what I was going to say is the other place that you might look for specific, for Vishnu, for specific help with this problem is in the user-generated text workshop, which is going to be, I think it was accepted this year. Okay, so it already happened in 2018. Because this workshop is specifically looking at noisy user-generated text, so things that are going to have a lot of, let's say, variation. So these papers might have some useful things for you. So, oh, Philippa had a paper. Oh, with James and Sharon. Oh, I'm sorry. They're great researchers. I like them a lot. Philippa's great. Yeah, so some of these might be helpful. Context-formed embeddings for noisy text might be useful depending on your downstream things. Paraphrase detection. You might be able to apply some of these things at the word level. This is probably going to be at the phrase level, but might help. Addressee taggy for detected task intent. But anyway, this workshop has run quite a few times, so you might find some papers here that are helpful that you might be able to apply. Yeah, glad to help. All right, and now Brian said some stuff, and I'm going to scroll up just a little bit. Nope, down just a little bit. I wish I could make the friggin' chat window bigger. It's so tiny. Oh, okay, there it is. Brian says, I used an analog of the CDC infection vector mashed up with Locard's exchange principle to track origins and spread of specific terms across political ideologies. Normally, this involves a hell of a lot of beating my head against Google and social mention aggregators. Could I port this in somehow to automate parts so I can track spread/origin across social exchanges, time axes, possibly geolocational spreads? Specific term across biology. So that I would actually, I can point you to the proceedings that are going to be relevant. So that is computational social science, political terminology spread, maybe? I know there were a bunch of papers about this at CSS last year. So computational social science is the field that I think this would fall under, potentially with a sprinkling of sociolinguistics, so more like computational sociolinguistics. Probably, actually, they probably wouldn't say terminology. They'd probably say something like vocabulary, and then it would be social graph. Visualizing computational social science, computational text analysis for social science, graph database for structuring human knowledge. It's going to be WordNet probably. Sorry, you got me off on a little bit of a tangent. Could you automate parts? Yes. Dynamic graphs, if you're looking at a time axis as well, is going to be the thing that you are interested in. Political blogosphere is an example, and how social representations theory is a guiding framework. We explore how visualizations complicate public understanding of new science. Discussion of best practices for protection images for public consumption. Brian says, sorry, came in halfway. Recently started diving into data science analytics, but I've only got comprehension of minor methods so far. I'm an old man using old methods. Oh, no worries. Old methods were great. There's still really good speech that uses speech recognition that use hidden Markov models, which are in no way neural, even a little bit. I would actually recommend you look into Kate Starbird's work on hashtags. She does really interesting work on sort of drift of hashtags within political communities. So I would recommend her work. And I think you'd find a lot of really good, what's the word I'm looking for here? Really good leads to other papers there. Yeah, I'm a big fan of using knowledge that other people have already created so that you are not rebuilding the wheel, basically. Yeah, sorry, tangent. Very interesting, though. So, stemming. And I guess also spell checking would be under normalizing. And I have actually somewhere fuzzy matching data cleaning 5-day challenge. I have written here we go. A kernel on how to do fuzzy matching for identifying spelling variation that you might find helpful, Vishnu. But it is in Python. I don't think I've done a fuzzy matching in R kernel. Someone might have. Let's see if we can find a kernel on fuzzy matching in R. I know there's a bunch of let's see, fuzzy matching, but also that's not how that's spelled even a little bit. I only want things in R. There's no R in matching. Tag to title content matching in R, that might be helpful. Playing with fuzzy, that sounds like a package that does that. Fuzzy clusters, predicteds of a match analysis. Some of these are match in a different sense. So this is a good example of sense disambiguation, which is where the word spelled the same way is actually a different word. So the canonical example is bank, like riverbank, like the soil and rock that's next to a river, as opposed to bank where you put your money bank. So that is another problem in counting things. Let's see. What libraries you're using? Let's look at the code. Okay. Oh, TM is a text mining package in R that might be helpful for you, Vishnu. Brian says, it's been emergent, but seems like most projects with this goal are all very tight-lipped to anyone not carrying currency with .edu or .gov. Yeah, I guess I can see that. I definitely have seen a lot of open science research on this topic, and that just might be who my friends and social network are. I would look into the computational linguistics literature. Actually, let's see. UCL. If you are also interested in a specific task or looking for the state of the art in computational linguistics, don't go to Archive. Archive is not peer reviewed. There's a lot of very, very crappy work on Archive where they have, I shouldn't say that. There's a lot of well-intentioned but in need of polished work on Archive. What was I looking up? Semantic change, political. The ACL anthology is free. It is open source, and it is the canonical place to find work in computational linguistics. So this might be a useful paper. I don't think I know Paul. We might have met at a conference. There's a lot of people in NLP, so I don't know everybody. But it looks like neighborhood subgraphs of particular sets of query terms. That sounds like more or less what you're looking at. Force-directed layout of the network highlights conceptual structures as terms connected by many relations are drawn together, and the user can select which subsets of relations and subcorporate to display. Okay, so this is just sort of a visualizations paper rather than a detecting of change paper, but still might be, helpful. And the reason I looked up semantic change is that's what happens when a word's meaning changes over time, and a lot of political terminology is very fast changing, so I thought that might help narrow it down. And I am getting really off topic again. Sorry, guys. This is just interesting to me, so I'm like, I'll go down this rabbit hole. Okay, so far we've talked about words. We've talked about tokenizing, so splitting into words and then counting them. We've talked about stemming, so figuring out which words share the same root, and then again counting them. Mostly, you just count words in NLP. That's the dirty secret. And then for it's not a dirty secret. It's just a lot of complex techniques just are counting things and then counting things in a slightly different way and then counting aggregations of things. So if you've heard of oh wow, loud seaplane. So if you've heard of vectors or embeddings, that's just counting how often two words occur together within some sort of span that you're specifying. So like in the same sentence or in the same passage or in the same book. And that's all that is. It's just counting things. That's all NLP is mostly. So these are pretty much the things that are gonna get 90% of people 90% of the way there in terms of getting a text into features that you can work with and feed into your model. And if you include Engrams, so looking at sets of words together, or whatever you've tokenized in, you can also get a little bit of syntax. And this will work for things like topic modeling, sentiment analysis, a lot of common tasks. It won't work for things where structures and meaning of sentences is more important. So things like question answering, things like chatbots, things like a lot of sort of high quality machine translation techniques. Things like things where you really want pretty much any place where you're going to produce text, it's much more important to think about structure. And if you want to get nuance and meaning, you're also going to care about structure. And that's where it gets a little bit more complex. So words are great. Sentences are a little bit more challenging. And the reason I say that is it's pretty easy to say, okay, this is a sentence. Okay, these are the words in the sentence. It's much more difficult to say, here's the relationship between the words in the sentence. And I think I have lost my page where I had speech and language processing, where I had the thing. So here's the new book if you're interested. Vector semantics, that's what I was talking about. It's just counting things and how often they occur together. That's all it is. And obviously there's a lot of fancy engineering to make it, doable and fast, but the basic idea is pretty straightforward. And then we get to all of this nonsense. So let me find a parse tree. In order to represent the relationships between words, linguists use a tree structure, which if you have a software engineering background, you might be familiar with binary trees, red-black trees, any decision trees in data science, random forests, which are ensembles of decision trees. This sort of general idea comes from linguistics, actually. Y'all are welcome. Chomsky developed it. Well, he didn't develop it, but he sort of applied it into a more computational structure. And this is sort of a very traditional constituents-based parse tree, and constituency means the relationship between words, where some of them are closer to each other and have a stronger relationship, and also there's a hierarchical relationship here. So the and ball have a stronger relationship than John and ball in the sentence. And hit has a hierarchical relationship where it's sort of over, in some sense, the ball. And John has a hierarchical relationship where sort of over, in some sense, hit. And we can see some examples of things that, oh, that's a bad one, sorry, that are more I'm looking for something with conjunction and I don't see any, so just ignore it. No, you don't want to see that. So the basic idea is that there are sort of chunks that you can do things, and if you want to display this relationship, you can create this tree structure that describes the relationship between words in a sentence. The complexity here, and there's a lot of complexities. So this is conjunction. So you can see that there's two structures and they are joined together by this and. We don't really know what's going on in our heads as humans. We know there's things like if you change the noun, you have to change the verb in languages like English, where the noun and the verb go together. So I would say, no, I'm trying to come up with a good example. So I would say the dog eats. And so there's agreement between dog and eats in terms of being singular, but the dogs eat. So those are both plural, eat and dogs. And in languages like French or Romance languages, you also have gender agreement, and you also have plurality. So there's additional, aspects. And then in, other languages, there's things like the sounds of the word will actually change. So a lot of Semitic and Middle Asian languages will also have a relationship that's at the sound level and not just the word level. So there's a lot of complexity, and we don't really know what's going on in people's heads. But the general idea is that you create this tree, and then it allows you to ask more concrete questions. And it allows you to do things like turn a statement into a question. So I ate the carrot. What did I eat? You have to know that carrot is what gets removed there, and you have to know where what goes in with relation to the rest of the sentence. I've taken a lot of syntax, which is the field that studies this is syntax, the way that the structure of words go on. Again, we're not entirely sure how it works, and there's a lot of ways to do parsing. So dependency parsing is one option. This sort of constituency structure where we talk about things being nested inside and other things is another option. Head-driven phrase structure grammar is another option. But most of these boil down into sets of rules that say you can have certain chunks that have certain slots in it that certain types of words can fill. So here's an example. I don't know, this is really small and hard to see. Open in a new tab. There we go. It's still really small. In the background, so this is, if we ignore the words at the bottom and we just say so this is a preposition, this is a determiner, an article, and background, we can take this same little structure and sort of like pop out the words that are in there and pop in other words that have the same part of speech. So we could say on a picnic blanket, or we could say around the campfire. And as long as the words have the same part of speech, it still makes sense and it's a well-formed sentence. For most data science tasks, you are probably not going to have to do a parse tree. The place where you may have to do some parsing is if you have really interested in talking about relationships between entities. So if I wanted to know, I had, a lot of meeting minutes and I wanted to know who assigned what task to who, then I might want to have a parse tree, and I might want to be able to say, oh, okay, this one was the agent, this one was the patient, parse it out, and then, fill those into the slots. Parsing is a headache. Some people find it, delightful, and it's obviously a fascinating research area. Not my favorite. I've probably taken more syntax than I wanted to. But it is something to know about. If you are getting into that, I would do more reading on grammars. So this is sort of the structure of rules that you use to generate these parse trees and to create parse trees from sentences, and do more learning there. And there's lots of parsers out there. So I guess the final thing would be 3, probably not needed. Parsing. I should actually probably indent this, huh? Figure out and represent the relationship between words. And obviously, if you're working with a parse, you are no longer working with something like a dictionary or a matrix. You are working with a tree structure. So there's additional complexity there. But those are sort of the 2 types of data structures that you're going to put text data into to use it. You're going to put it into some sort of matrix, some sort of dictionary where you have words or Engrams and then their counts. And perhaps, multiple dictionaries for like different sentences or whatever. There's a bunch of data structures. And then if you are interested in parsing and the relationship between words, then you're going to use these tree structures and you're going to represent them that way. Brian says, so you could assign emotional weight gravity to your parsing. Certain words and colloquialisms are considered to have greater linguistic firebrands effects when you do this from a pen and paper study. Usually when people are looking at affective text, so that's just like text that is showing or relating to some emotion, they're not going to use parsing. Most of those words tend to be lexical or word-based. This looks like I have never heard of this conference. 2011. Okay. Oh, okay. It's AAI. Okay. This is a real conference. There's a lot of more recently. There's some sketchy conferences out there. Many conferences are also very good. Usually when people are looking at affective text, they're not going to be using parsing. These are really for things where you the relationship between words is the most important thing, and the words themselves are less important. Yeah. This is not super good looking, so I don't know that I'm gonna make it available as a kernel because I don't know how useful it would be to people. But this video will be up, and you guys can feel free to hit me up on Twitter or on the Kaggle forums, and I'm happy to answer questions. And going forward, we will talk a little bit more about slightly more interesting things. I know this is a little bit esoteric, but a lot of times people bring me questions where they have all the skills like the regression, the classification to answer the question once the words have been turned into numbers, and these are just sort of the processes for turning words into numbers. And maybe next week, now that we have sort of the conceptual background, we'll go through and actually do the dang thing. And I think it's the week after that I'm actually going to be at a linguistics conference, so I don't know that I'll be able to stream. But yeah, thanks for joining me. I hope this was helpful for you guys. I had a lot of fun. I'm always happy to talk about language. But I do have another thing to get to, so I'm going to sign off, and I will talk to you next week.